So on behalf of NITheCS, I'd like to welcome you all here today, and Francesco sends his apologies. This is our regular Monday afternoon NITheCS Colloquium. Thanks those who are online as well. I'm Sandra McFadgen. I'm representing the NITheCS research program, Advancing Biodiversity Informatics and Ecological Modeling. And thank you very much to our Vice Chancellor here, who has just walked in. So I've shamed her into arriving late, but thank you very much for being here. And we're branching out of our wheelhouse a little bit today, and we'll have privilege to welcome Prof. Fabio Dercole, is that right? And he's going to talk about the integration of complex system dynamics at the primary school education level. But to give a proper introduction, I'd like to introduce Dr. Pietro Landi, who will provide a better introduction than I have. Thank you.
Thank you, Sandra.
Thank you, Sandra. I'm very privileged to introduce Prof. Fabio Dercole from Politecnico di Milano, where he's been professor since 2015, and I'm sure he started his studies long before that. He's also been a visiting researcher. Last millennia, actually.
Last millennium.
He's been a visiting researcher in many institutions, among which Cornell in the USA and Helsinki in Finland. And since 2020, he's also the president of the Italian Society for Chaos and Complexity. And today is gonna try and make that complexity a bit simpler for us and for high school kids, primary school kids. Where should I stand? Further away, okay. And yeah, without further ado, thanks Fabio for being here and looking forward to your talk.
Thank you. I need to use my glasses to see better from close.
Yes.
Yeah, because I put on my glasses and I move the microphone. Now, yes, Zoom meetings. Even before it took some time, but okay. No video. Yes, but then I mute it. It's mute. Should be fine. And then I have to share screen again. Okay. Should come. Don't need this. It's not yet shared. So it is shared, but not on the projector. It's coming. Yes. Okay, I think we are ready to go. So thank you all for being here. Thank you, Sandra and Pietro, for the nice introduction. And actually, I appreciate to be here. I appreciate this idea of the colloquium because, as far as I understand, these talks are kept more general for a general audience. And I think this is sometimes a very good idea. We are always too focused and too busy on our own researches that we hardly find the time to think about science more in general, and especially to science education. So having a colloquium every week, it is every week more or less, it's a very good moment to reflect, to think about more in general. And so I very happy and honored to be able to contribute to this colloquium. And well, one usually open these talks by thanking many people. I thanked already Sandra and Pietro, and maybe also Francesco that couldn't be here. You can tell him. But I would like to make a little bit a step back, and actually I feel that I want to thank you, your beautiful country, as an entire thing, because it's my first visit to South Africa. Actually, my first visit to Africa as a continent, and well, if I just tell you that you have a beautiful country, it's nothing new because you already know it. But I've been traveling 5 weeks in this country, and I did many kilometers, and I had such a great and positive experiences that I really think that I'm grateful to your country as a whole, from the stones to the sand to the plants and the animals, even the mushroom, because we had good mushroom. To speak about the three realms of biology, and humans. I mean, men, women, kids of any color, very great experiences in very different situations and environments. So I really want to thank you all. We say that when you go to Africa first time, Africa enters you and you can live without. I mean, we say this in Europe sometimes, and maybe it's very naive, very trivial, but it's something that happened to me, and so I'm really grateful to be here. So thank you very much. So coming closer to Stellenbosch, maybe I want to thank you, Professor Moyo, to be here, and for it's an honor to stay in your university. So thank you for attending. Then, of course, a great thank to Professor Kang Hui, who made my visit possible. He actually invited me for a workshop he is organizing starting tomorrow up to Friday. Maybe most of you know about it and will be also involved in it. It's a workshop on theoretical evolutionary biology, which is a field in which I like to apply mathematics. Many people do it, so I'm looking forward to attend and contribute to the workshop. So thank you, Ken, for the invitation. And actually, the first part of my stay in South Africa has been made possible by Sandra. So I'm deeply grateful to you because you invited me to Skukuza in the research camp to show me your terrific field work. I mean, terrific in the sense of the English meaning. Wonderful work. I have to say this. I think you have an infinite passion for your work, and I hope to be able to have just a bit of it, because mathematicians know that a bit of an infinite is still an infinite. That's a joke, bad joke maybe. And also you make me laugh when you try to speak Italian. You should ask her about Choco Chocolino. I have to say that. Okay. And then, of course, Pietro, I can miss to thank Pietro. Pietro is my anchor here in Stellenbosch because Pietro has been the first student I advised for a PhD in Milano in my career. After you got your PhD in 2014, and then he applied for a postdoc here. He came here, and I'm really happy and proud also that he showed his value here up to the point that you appointed him as a permanent staff. So I'm very proud of you. Okay, then thank you all for being here. So I made this thanking session a little bit long, maybe, but I really felt that I had to do it. Maybe I can make the talk very short, so we can enjoy the wine and the food soon. So my talk is about math education, which is not one of my field of research. I have to say I have no contributions paper in journals about education in science and in particular in mathematics, but it's a subject I've been thinking a lot in the last years, maybe because I have kids at school, but also after the COVID homeschooling, also was a reason to reflect on this. And so my feeling is that we teach mathematics too theoretically, starting from primary schools. Of course, we need the theory. We need to teach what is abstraction, theoretical thinking, both the algebraic and the geometric views of mathematics. But what we are missing, I think, dramatically, is to show what you can do with mathematics, to show it is powerful, to show it is useful. And I start thinking that we can do it even from the beginning, from primary school. And then I started developing locally in my town with the primary schools in my district, especially essentially my kids' school first, and then a few other schools, activities to integrate the standard programs and to together, of course, with the teachers to show applications of what they learn. So today, what you will see is just an example. What I did so far, I developed a few of these activities, which are, of course, recasted in the form of games that kids have to play, because you have to show them application, I believe, but you also have to involve them to work on applications. They should do it with their hands. Sometimes I use Lego bricks or other mechanical tools, but the one I show you today is a bit more, maybe theoretical is not the proper word, because we want to show applications. So what I want to do is to show through a game, through an example, which is reinterpreted as a game for the kids, that mathematics can explain very complex things with very simple rules. So complexity is the results of, it's most often the results of very trivial rules, which are connected, which are repeated in time, and the result is complex, but the rule governing the dynamics is very simple. So you have to take it just an example. It's an example activity that you can play in primary school. Actually, this one requires plus, minus, and multiplication between positive integer numbers. So maybe we have it in 3rd grade in Italy, especially the multiplication with numbers including at least 2 digits. So this is meant to be for 3rd grade, but actually I did it also starting from 1st grade in a festival that is the one that you see in the logo. Festival dell'Ingegneria is the festival of my college. Actually, I'm working in a Polytechnic college. So polytechnics in Italy, they can deliver degrees in engineering, architecture, and design. So we don't deliver other degrees. Then we have University of Milan, which is delivering all the other degrees. So this was the feast of only the engineering school that my college is organizing every year at the starting of the academic year of the fall semester. And we always organize, it's on Saturday, we invite families, prospective students, families, and the students as well, and also the students enrolled, they help us. And we also organize activities for kids. Actually, this is the t-shirt of you see the same logo. That was 2022, where I did these activities for kids also starting from primary schools. And we have it also now in these days, but I'm here, so I cannot contribute this time. So this is a very well-known example, but I don't want to spoil you the result. It's a very well-known example in mathematics. So now you will think about, while I'm presenting this, that I reinterpret as a game, as I told you, about a cell. The kids study cell biology, I mean, an introduction to cell biology in 3rd grade, so they know what is a cell, they know living things are made principally on cells. And this is a plant cell, as you see, because it's green. It is wandering and clumsy. Now I'll tell you why I choose these names. And she's dropping daughters each time she moves, or it moves, but let's say she moves, it's a mother. Okay, so let's go. We also give a little bit of introduction, very trivial, very short, to explain the motivation why we want to do complex system dynamics in primary to the kids. So essentially we tell them, look, you are studying math, you are struggling to study math, but math is the language of science. So if you want to understand nature or do science in general, math is the language. And it's very powerful. Essentially the power, I see the power in the fact that it explains complex things like the one we are going to see today, but as a result of very simple rules. And the simple rules that you are learning is plus, minus, times. These are the simple rules. To apply math successfully to describe something like nature, you have to do it in a smart way. And smart means that sometimes you don't need to be very precise. You have to be able to grasp what is important and leave what is not important. And this is the art of math, of applying math. It's very difficult to realize in a model what is important and what is not. But this is something you have to think about. Make simplification, make approximation. You don't have to be always complete or precise. And when you cannot explain things to the end, just describe them on average, randomness. Make a random description. So sometimes you approximate and sometimes you lead things to random events. And that's why my cell is wandering, because, well, actually clumsy. Clumsy means she's not very good in doing computation. So don't worry if you're not the best in doing computation. Approximate, simplify. So you can be a little bit clumsy in doing your computations. And then the randomness is the wandering. This cell is moving, but is moving, you will see in a minute, a bit randomly. Okay, and then this is the motivation. Then we want to describe what this cell is doing. And the cell moves in a plane, but we cannot use Cartesian plane to 1st grade kids. So we tell them, you have a ruler in your pocket. So now we are playing with 2 rulers. We have 2 rulers with positive numbers from 1 to 200, 1 to 200, like 20 centimeters, 20 centimeters. and we give them this paper in the maximum size of a printer we have is A3. You also have A3, but you couldn't get it in color. But we give this, well, you have this plane and the rules. Now I'm coming to the rules. And this is what they used to play. We also give a green marker and a dice. A dice, a special dice they love, is a dice with 10 faces, number from 0 to 9. People playing Dungeons and Dragons, they love such a dice. Okay, so this is the setup. There are a few color prints smaller in A4 if you want to play home. Okay, then we explain position. The cell is somewhere in this plane. And so let's call X, the position on the horizontal ruler, and Y, the position on the vertical ruler, but this is very trivial for you, so I can speed up. For example, if the cell is in position 124 on the horizontal ruler and 70 on the vertical, we play the battleship. The battleship, no, you call it battleship. So we do a straight line when the ruler is 124 and a horizontal line when the ruler is 70, and at the crossing with the marker, with the green marker, you can fill a little square, and that's our cell. That's where is now our cell, the mother cell. So that's position, coordinates. And then what does the cell do? Well, duplicates, leave a drop a daughter, and move. And have you seen the daughter? I go back. Look at the mother cell. Duplication. There is a little daughter appearing and wobbling. That's the daughter cell. Well, daughter cells can actually also reach maturity, have a cycle, duplicate, and move, and the results you will see won't change. So let's, for simplicity, assume that the daughter cells just stay where they are, but if you let them move and duplicate, nothing is going to change, believe me. Okay, it's duplication and movement. And how does the mother cell move? According to 4 rules. And maybe these are the 4 famous rules. Okay, but for kids, rules have to explain in a very simple way. The rules gives you the new position. Starting from the current position, the rule gives you the new position, the new X and the new Y. And then you compute the new X or the new Y with some simple computation. I promise that there would have not been division. There is division here, but this is where the clumsy nature of the cell will play a role, because the only division I have is divisions by 100, and we will simplify them. We will approximate because our clumsy nature. So forgive me for the moment that I have this division. Okay, so at the right-hand side of the equal sign, X and Y are the current values. You plug in the current values, and you compute the new values. And then you move your cell. That's the game. But I have to tell you, how do you choose the rules? And that's the randomness part, the fate. We leave something to fate. But before doing this, let's apply those rules to warm up, because with the kids, you have to warm up. So let's now start with the cell in position 100, which is here. Maybe I can use the laser. It's just at the bottom here. Maybe you don't see here, there is a little square filled in green. But I tell you, you can start wherever you want, and the result will not change. Okay, you can start wherever. But we start for simplicity in this point. It's down in the middle. Then let's say the cell decides to apply rule number 1. Then you have to plug in the current value. On the right-hand side, there is no X. There is only the Y in the second equation, you see? So instead of the current Y on the right-hand side, we have to plug in 0, because the current Y is 0. So we just plug in 0, and then it's an easy computation. The new X will still be 100. The new Y will be just 0. So the cell doesn't move. Okay. if she decides to use rule number 1, she doesn't move. But okay, it doesn't move, it's 0. But let's assume she decides to use rule number 2. Then you have, again, to plug in the current X, 100, the current Y, 0 in the right-hand side. You do it step by step. Okay. Then you make a multiplication, another multiplication, another multiplication. Okay, here it's a bit difficult because it seems that there is a negative number. It's not a negative number, it's 400, but then 0 minus 400 for kids is very difficult in 3rd grade. They don't understand it. But still, you can explain. You will understand it next year. You go to but with the ruler, it's very easy. So minus 400 is a position at the left-hand side of 0. But this is actually in the Y, so below 0 in the vertical. But it doesn't happen actually because then we have to divide by 100. And this is an important point. How do we divide by 100? We want to simplify. We take the integer division because we don't want to mix up kids with decimals. In 3rd grade, they only know integer numbers. So we apply the integer division. We don't call it integer division to them, but to you, I can tell you. So we simply drop the units and the tens. Dividing by 100, it's more or less like dropping units and tens. So you simply cancel. So division by 100 is approximated by dropping units and tens. You have a number, you just cancel the units and the tens. You throw them away. So it makes the division by 100 very easy. And so we have minus 4 plus 36, which ends up in a positive number. So we don't go below 0 or at the left of 0. We remain in the positive plane. And we have the new X and the new Y. So now the new X and Y are different. The new X is still 100, but the new Y is 32, is a bit above. So now the cell is moving somewhere here. Maybe you see now the cell is here. And then from there, if we use number 3, I can go a little bit faster with you so we approach the wine and the food. Now we have to plug in the current value. So X is 100 and Y is 32. We plug in the current values, we do the computation. Very easy, more or less easy. I mean, big numbers for kids, but still they can do it. And then our division by 100 is very simple again. We drop units and tens. Okay. So we have 11 plus 80 and 30 plus 9. And we get the new position, 9139. We update our coordinate here. I missed an S because coordinate, I left this in Italian. So in English, I need an S at the end. And here it is, the new position. It's here. Then, okay, computation, I trust you. You can do it. You can do them. But how do you decide which rule to use? And that's the wandering nature of our cell, the randomness. She just decided at random using a nice dice, the 10-face dice I told you about. You throw it twice, you get a number from 00 to 99. Okay, they are equally uniformly distributed in probabilities. Each number has 100 probabilities to show up. Of course, I'm telling to you, not to kids, but you throw it twice and you get a number from 00 to 99. And then our cell is a particular one that decides in this way. Only if you got 00, so 0, you use rule number 1. If you got from 1 to 85, you use rule number 2. If you got from 86 to 92, I mean, this is just weird numbers. It seems to be very weird numbers. Seems that I plug in those numbers at random. But even the coefficients in the equations, they seems to be there just by chance. But still, it's a nice example. I told you, very famous. And only if the number that you get from the dice is in between 93 and 99, so not very often, but sometimes you use rule number 4. And you can even introduce in a nice way the concept of probability to kids, because probabilities is the ratio between the number of success between the number of possibility by the number of possibilities. So we have 100 possibilities from 00 to 99. And so rule number 1 has only one chance to be used if you get 00. So the probability is 1 over 100. It's a fraction. Well, fraction, they arrive in 4th grade, but still, you can say you will see next year. There are 7 possibilities to use rule number, no, okay, let's say rule number 2. There are 85, that's the most common. The cell most often use rule number 2 because there are 85 possibilities over 100 to use it. And then 7 and 7 equal probability for the rule number 3 and 4. That's it. And now I let them play for maybe 10 hours. No, actually, what I do is I go maybe maybe 4 or 5 months before the end of the year. I present the game, then I leave the material and ask the teacher to let them play sometimes during the break. And what happens actually is they just use the dice every day, every time. And the teacher got crazy because even when he's explaining other things, the kids are using the dice because they love it, the dice a lot, the 10 paces dice. But still, so they are a little bit angry with me for that. But at the end, maybe after a few months, I go to give another class, to another lecture to the class, and we discuss what they got, and then I show what I can get with a computer. I have also an application of rule number 4, but then it's too trivial for you. You apply rule number 4, and the cell, if after applying 1, 2, and 3, you apply 4, the cell reaches this nice position down here. But you have to continue then. And that's the end. But so after a month, I look what they did, and then we go into coding, because then I let them understand that this is a kind of games that a computer is actually good to play better than we are. And so I want to introduce them to coding a little bit. And it's not that difficult, actually. They are very smart. What do you think they understand if I say that x at time 1, x, maybe you can read, maybe you can make it a little bit bigger, but I don't know if I can. I have to change the font size, which is a bit complicated. Can you read it? So I emphasize in this way. So if I say x at time 1 at the beginning is 100 and y at time 1 is 0, they understand it's the initial position. And then for many times, like 100,000 times, they in 4 months, they hardly did 20 points. But this is 100,000 points. We throw a dice. It's a dice, a special dice that the computer can do from 0 to 99. It's just one big dice with 100 faces, virtual. And then if the dice is less than 1, that means 0, we use rule number 1. Else, if the dice is between 86, but at least 1, because if we skip the first option, it means that the dice is at least 1. So between 1 and 86, we use rule number 2. And if it's less than 93, but at least 86, because we skip the first 2, so between 86 and 93, we use rule number 3, and so on, and then number 4. And then of course, I have to explain. You see, the computer here makes the real division, not the clumsy division, the real division. So if you want to be clumsy, we have to round off. We have to drop the decimal, and this is done with this fix command fixes numbers. So essentially remove the decimal. And so with these 2 last commands, the fix, we have the clumsy cell. If I comment out this, we have the real cell. I mean the professional cell, the pro cell, the pro version of the game with decimals. But let's stay with the easy one. And then I plot the dot. This is just a line, but it's not a line, it's a command that plots a dot. So they had the idea of what is coding for scientific computations. Then we are done. We can run it. I have another script that I don't describe usually to kids, that only draws the grid. If I run it, so this is the grid. I have a comment, but okay, you don't see it. It's a comment by Zoom. Well, maybe I can move it. No, I can close it. And then, are you ready? What are you expecting? It's a plant. And I know that my mathematician friends, they already know, but it's a cell jumping, dropping daughters, and building a plant. So we go back to our code. We run at 100,000 points, starting from that one. I run. I go back to the picture, and it's a fern. It's a fern. It's a plant. The cell is moving randomly. And if you change the initial condition, again, the same fern pops up. And if you throw dice another time, of course, it's a different construction because you don't select the rules in the same order, but still it's different construction of the same fern. So mathematically speaking, to be more theoretical now, this is a piecewise linear system, piecewise linear dynamical system, because if you now go back, well, we enter technical details, these are linear equations. The new coordinates, the new x and the new y, are just a linear combination of the previous ones. So the simplest dynamics you can imagine, a linear one. The new coordinates are linear combinations of the previous ones, but we have four linear combinations, 4 linear systems, and we use them randomly. So it's a stochastic piecewise linear system. It could actually be made deterministic very easily. You know, Pietro told you I'm the president of the Italian Society for Chaos and Complexity, and chaos is the keyword, because a deterministic chaotic dynamics can be as similar as you want to a stochastic process. You can approximate as good as you want a stochastic process with a deterministic chaotic dynamics. And so actually I did it. I replaced the dices with a logistic equation, with some people know it's an example of a chaotic system. So we have a chaotic dynamics, which is deterministic. Once you fix it, the initial condition, the future is just one. There are no dices, there are no random events, just one trajectory. And that trajectory is driving the choice of the rules from rules 1, 2, 3, 4. And the same fern pops up. That's actually a good example, but maybe at master level, to show that a stochastic process and a chaotic dynamics are two faces of the same coin. What changes is the way you describe your system. If you know the rules, the mechanical rules, the mechanicistic rules, you can describe with using deterministic equations. If you don't know them, you can have a black box approach. You take from data, you fit a stochastic process to your data, and you describe the same phenomenon. If you know how it works internally, you can try a physical model, a deterministic model. If you don't know, or it's too complex, you can try a stochastic approach. But the deterministic and the stochastic are just the way you model reality. The reality is not either one or the other. The reality is just reality. I mean, unless we don't go to philosophy or speak about metrics. But what is deterministic or stochastic is the model you use to describe it. And you can, this is stochastic, but as I told you, we can make it deterministic as well. So it's as it is now, it's as I told you, it's a stochastic piecewise linear system that has this fern as a unique global attractor. It doesn't matter the stochastic realization, it doesn't matter the initial condition, it always, the cell is always building this fern. which is a fractal, of course. Then we can speak about fractal geometry. It's a complex example, but I think it's just a good example to show kids that very simple rules can build complexity. And this is it. Maybe it was too short.
Thank you so much, Fabio. That's wow, that's such a nice way of illustrating what we in our group know already, that the mathematics is integral to actually understanding complexities in nature. And
maybe in the meanwhile, I
ideas.
can comment the two clumsy comments.
You mean on the Zoom?
No, on the MATLAB.
Oh,
I can comment in the code the rounding, the fixing, and I can redo just to show you the pro version of the firm. And then, of course, I'm open to take questions. Now it's the pro version. No, I open another. I have to go to the other script. This is the pro version. This is the clumsy version, more pixelized. This is the pro one, using decimals.
Thanks so much, Fabio. I'll open the floor to questions.
Thanks, Prof. That was really interesting.
Thank you.
Um,
Maybe too trivial.
what age group you said? Grade 3s or
8 is we 6, 8, between 8 and 9.
okay. And just out of interest, have you thought of speaking at any schools while you're in South Africa?
No, not in so. Say it again. Sorry. No, I didn't think about.
Because I think, I mean, we find it extremely interesting, but I mean, to expand on this kind of knowledge, you also need to breach that gap between academia and working with actual children that this is geared towards.
It's a challenge.
I have a lot of teacher friends, so if you are here and you have a little bit of time, I'm going to be part of the workshop.
A tour. But I can come another time also. I will be happy.
That was great.
No, so far I tried with my kids' school first as an example, as an experiment, and then I extended it to other schools in my district, not even too far in my city. And then I I applied for a project to our Ministry of Education to have funds to plan these activities more regularly, to maybe insert in curricula, or even having more regularly in other schools, of course, involving other colleagues, or maybe even thinking outside my city, other cities, or making national-wide. But so far, I didn't get good money to do this. But it's an idea in progress to have money first, because as you know, without money, you don't do much. Actually, you have to realize that all these activities that I design and implemented in schools, they are very time consuming. I mean, I invested quite a lot of time, because this is just one, but I have a portfolio of 3-4 activities so far, and then keep thinking, always thinking on new ones. But this is an activity I do for no extra salary, and actually it has a negative effect on my career, because we are only, as you know, our progress is evaluated only on bibliographical numbers and money. It's only bibliographic, at least in my university, is bibliographical numbers and money I bring in. So if I bring money in with these activities, is good. But if I don't bring money and I don't publish, I'm destroying my career doing this. No, there are scientific educational journals. I'm thinking of maybe exploit this, but to reach those journals, at least I have to collect some data. So far, I collect feedbacks from kids and from teachers, personal feedbacks. I mean, comments, direct comments, or we have questionnaires that we hand to kids and teachers. But to publish on educational journals, we need some more data and a little bit of statistical evidence that this is appreciated and has an effect on the ratio of students that then go for STEM subjects in university. So we should have a control group having traditional math teaching, another experimental group having these extra activities in the curriculum, and then check in the years to come how many they go for STEM subject or not in the university, if there is a bias or not. I mean, this is sounds to be a very long project. It takes years, maybe 10 years. We heard a very wonderful talks a few days ago of a project that lasts 30 years. But these are very difficult projects to run.
Sorry, so thank you so much for the presentation. I just wanted
Honored.
to check. So in the for this type of exercise, would the students be plotting not on the computer but using their
Yes.
spreadsheets?
We give this.
So they do it manually, right?
They do it manually, of course.
Okay,
And
so-
they have a green marker to point, to draw the position of the cell.
Okay.
They have a dice to random generate numbers.
All right.
And they just throw the dice, select the rule among the four. They do the computation by hand. And then maybe I bring my students to assist them, maybe with a calculator. So if they make it wrong, they can just help them.
All right.
But it's essentially all my activities are thought to be done manually. Also because of restriction, maybe if you could go to a class with 20 or 30 tablets, maybe we could actually implement apps specifically to let them play the activities on the tablet. But it means buying lots of tablets and also developing the software, the app on purpose, which is in something I'm thinking about, but I need people and money to do this.
Oh, excellent. No, but I just wanted to check. So in the Italian system, the teachers who teach in the primary school, I'm assuming that they would have a degree in mathematics. How does it work in your
Not the teachers. They need it's by classes. I mean, if you want to teach in primary school maths and science, you can do it with certain degrees. Like even a degrees in engineering is good, or a degrees in maths. But it's not good, but not enough. You have also to have a special degree for teaching. That either you do the teaching, there is a specific school for becoming a teacher, or if you have a degree in engineering or math or physics, you cannot teach in primary school. You can teach in high school, but you cannot teach. For primary school, you have to go through a special school to become a teacher.
Thank you, Fabio. So I suppose you have already done this before. So if you incrementally mutate your parameters, and what kind of leaves going to emerge?
If you change them slightly, leaves that are not nice as this one. Essentially, it was the guy who did that. It's in the book Fractals Everywhere. They were the first fern. It's in that book by a British Barnsley. Maybe I forgot exactly. I'm bad with names. Barnsley, I think. And so probably he did this work. He did the full sensitivity analysis to find out the best fern, because I tried to change them, not mutating during the course of a simulation, just changing them and redo a new fern. And the fern is never nice as this one. So it seems that he selected the best parameters, but nature did it by evolution. I mean, we have the fern, and this is such similar, such a good one, that means that those numbers, the weird numbers that I show you, somehow they are in nature.
Which means you only need to mutate slightly to generate a very much diverse.
You mean there is sensitivity with respect to parameters? I would say so. Yes, it's sensitive to parameters.
So you also have a new kind of a
bifurcation, another
bifurcation analysis. Yeah, it also can have evolutionary modeling.
Yeah,
in those.
at a certain point, there is a critical parameter values in which you get a cauliflower, because the cauliflower is also fractal. Thank you.
Any other questions? All right. Thank you everyone for coming, and thank you, Fabio, for that amazing talk. if I'd done this in 3rd grade, I might have studied mathematics instead of ecology, maybe.
They've escaped. No,
Thank you very much, and thanks for everyone who came. The people online, I'm not quite sure how those questions get answered.
should I control the chat? I don't know. Chat. 13 comments. Thanks. No question from me. Thanks.
All right. There was someone online who raised their hand. If she's still there, please go ahead and speak.
Yeah, seems everybody's happy.
All right, thank you.
I'm around until Sunday, but the workshop we can organize is in a Louvain farm. So maybe I won't be too much around in campus, but if you write me an email and you want to talk, I'm here until Friday for sure, and then maybe even sometime Saturday and Sunday.
It's clear that you definitely have to come back and
Yes,
get
I
some
would like
skills
to
as well.
But we are actually, I mean, maybe I didn't mention that I was not working actually with Pietro in the last years because also for reasons related to my career, because I'm in a Politecnic, so we don't do much research in evolutionary biology or ecology. So for career reason, I had to switch a little bit my research topic in the last years, but now we decided that we have to work again together. And this is also one of the reasons I'm here, and we are already starting new projects. So I will definitely be linked to Stellenbosch again. And maybe we can even think of some exchanging students or setting up some exchange programs. I mean, double degree, we are open actually. We have programs with double degrees at master level and PhD level, not bachelor, I think. And we can think about maybe we can open a better connection.
Thanks so much. So let's chat about that further outside. There's some refreshments for everyone to join us. I'm sure you can have a chat personally to Fabio. And thanks everyone again. Thanks, Fabio.
Thank you. Thank you very much.